Alright, we're set. So, in today's video we're going to talk about this power monitor. And first things first, I want to mention Great Scott's YouTube channel and Great Scott himself for inspiring this video and this project. Well, first this project and then the video. So he actually made a video about a very similar power monitor about like a year ago or so. And I flipped the fuck out. Like, it's what I've wanted forever. In the meanwhile, I have gotten a pretty badass USB power monitor. This YZX Studio, what is it, ZY1276. And I've also gotten a Ruideng one, but anyway, this is something else. And the reason why this is something else is that this is internally powered. And I could program the UI. So if you've seen my previous videos, I really disagree with the way they've done the UIs on the commercial power monitors. So in this one I have made my own, right? So there's a few modes. This is the screen off mode where the all the LEDs except the power one are turned off. This would be just the amps, right? So you have a simple A meter, and what I'm also a very big fan of is having the decimal point, only the decimal point, right, when displaying a comma value. So not having this redundant zero at the top. I think it just looks fancy and shit, and yeah, why not? Also, given that we're displaying amps, I very much enjoy having just 3 decimal points. All of these commercial ones have another digit. Oh my god, all of them have this 4th digit, which, I mean, it's not bad, but then just give us milliamps, comma, the extra precision you have there. Or I would rather just forego it and just, yeah, anyway. So this would be the amp mode. This would be the first power monitoring mode, right? We have volts, amps, and the product. This would also have the accrued values of milliamps and milliwatts, right? So we have some values here. We could reset these, press the button, and as long as you keep it pressed, we're displaying this. We also have a max mode, right? Why not? And a serial mode in which we're sending the data via the serial output once a second. So we're sending, I think, volts, amps, watts, and I think we might actually be sending the milliamps and milliwatts, because milliamp hours and milliwatt hours values, because otherwise you'd have to do a lot of digging around in Excel to compute those, and there's absolutely no reason. And the last mode is just displaying the battery. And the display off mode when you want to do a measurement and you don't fancy wasting a lot of energy on the display. Alright, so let's quickly first talk about the number formatting, and for this I have prepared a demo mode. So a device under test mode is what that stands for, which basically injects random values, if it would work. Alright, why didn't it work though? It does work now, anyway. So basically the way we're formatting this is we have values, right? And we might actually have to cut those, right? So actually in this case we're not doing it. All we're doing is displaying the dots, right? Aligning for the dots, first of all, right? That's also something. So when you have a 2-digit number here, the dot is also aligned. Over a limit for values that are above what is rated for the INA219 chip inside. We're actually going to go over the schematic and the code as well, also in this video, so if you're not, I'm just showcasing what it can do now. Okay, so that was roughly decent, right? However, in this view, please note that we only have spots for 2 decimal points, right? And if we're displaying 12 volts, then we have space for only 1 decimal point, right? Such as is the case, for example, down here on the watts. Exactly, and that is a pretty, well, it's not difficult, but it's a very tedious thing to do, right? So I have a whole function that formats numbers, because if I have, for example, 23.86, then I'm going to display 23.9, right? So I'm going to round considering the next decimal value, kind of. And that is not trivial. And also in this view, the dot will move because there's absolutely no, I prefer having the extra decimal point than having the dots aligned, right? So that was a decision. And something else worthy of note is, do notice that these values are centered below their headers, their titles. This again is very, very tricky to achieve. Again, it's not anything, right? It's just a bunch of little functions, but it takes a long time to actually align it so it's pixel perfect, or as close to pixel perfect as it can be, right? So 3 values might not center as well as 2 values, or vice versa. But yeah, and also when we will jump the 1000, which should happen soon, I also added spaces to separate the to make the numbers as readable as possible. All right, let's see. Also worthy of note, the font sizes are not as big as they could have been, right? So especially in the other view, so in this view, right, it could have been definitely bigger, but that would have required, at least with the library I'm using, redeveloping a font, or I've done this like almost a year ago by now. And so I don't remember exactly what the problem was, but you can see there's definitely more real estate, but the next size up font would be too big, right? And so you'd need to render a font for the it was too much work. At some point it was too much work, right? The UI actually took probably more time than the whole thing, than the whole construction. And so you could definitely do that, and I will maybe next time, right, actually render a font that fits such a screen more precisely, but it's not too bad, right? For example, here there's very little wasted space, so it's more or less okay, right? The only wasted space is in that other view and maybe here vertically. So actually, let's get back to this. As you can see, I'm also adding a space for the thousands, and this goes up very high, so this can go to, I think, I'm not sure, but I think it can do millions. So it shrinks the font size down, and it actually to, I think, the same size as the milliwatt and milliamp headings. And then it could do, I think, 9,999,999. So yeah, I think that pretty much wraps up. Oh, there's a little Easter egg, but it's not very usable because this display is complete shit, so. Alright, so it's an inverted view. Again, in person it doesn't look this flickery, but anyway. And you can see the problem with this view is, actually I don't think you can see the problem. So the problem is when you have, yeah, you really can't see it. Problem is, for example, these lines have a lot of pixels off, and so they appear a lot brighter than the rest of the display. You can see this a lot better in person. Let me see if maybe I can adjust this a bit. Yeah. Now it's a lot worse in person. Maybe now, yeah. Anyway. And obviously it's supposed to remember all of these values and the mode it was on when you turn it off, right? So let's see if it works. It doesn't remember the glitch mode, the Easter egg inverted mode though, because I don't know. Yeah. So let's test that out again. Oh, let's actually test the max mode just right quick. We have to be in one of the 2 first modes to enable the device under test mode. And also focus. So the max mode displays the max watts, the max amps, and the max volts. It doesn't record the max volts and amps and then the computed watts, right? So you could have 2 values here that multiplied do not equal the watts, right? So you can have like 1 volt and 50 amps, and 50 amps and 1 volt, and it's going to be 50, 50, 50, for example. And the autofocus is out for some reason. But yeah. So next up, I think we should very quickly go over the schematic, and also should we open it? No, I don't know, I'm not gonna open it. Although yeah, why not? Let's open it. I'm not gonna completely tear down because the jacks are actually prevent holding the board in. On the bottom I have, first of all I have the explanation of the modes. I really would enjoy autofocus to work though. Oh man, that is so stupid. Focus is back up. And yeah, so we have basically the modes and what the buttons, what the long presses do, right? The short press people will figure it out, right? This is basically for future generations. Okay, so let's get this open. Okay, so let's actually zoom down on this. Try to use the paper as a rough indicator of where I am in shot. So basically what we have in here is a lot of wires, first of all. I really should stop pointing with the metal shit, but anyway, one last time. Okay, so we have this TP4056 module, which is charging and protecting the batteries. Or does it protect them? No, it actually doesn't, does it now? Yeah, so we have a simple TP4, I'm sorry for the angles, but yeah, work with me. So we have a TP4056 module with no protection, charging two PlayStation controller batteries that are tucked kind of like this and like this below. We have an input wire here, right? So the batteries go kind of like this and like this. And this is, I'll link all the products that I've used in the description, right? So this would be the Mini B female panel mount connector. That is actually something that I was supposed to discuss separately to the data. So I made the schematic just to avoid having to manually draw it. It's not supposed to look cool or be converted to a PCB or anything. Anyway, so what I'm doing with the USB is I'm taking the power wires to the TP4056 module, right, and then that goes to the lithium-ion battery and charges it up. And the data wires, so D plus and D minus, excuse me if it's the other way around, I am actually taking to the Arduino, right? So D plus and D minus. So this basically does double duty, right? And you would have to have it powered on, have the device powered on to have the Arduino get power and also data, right? So yeah, it's not very nice to just connect the data and have the thing dead, but it's fine. It works fine, right? It's no problem. So now that that's out of the way, we could basically go hand in hand with the schematic. So we have the battery, right? So we have the USB in. It goes into the TP4056 module. You can see I took two wires from below, over here and over here. Then that goes over to the battery, to the two batteries, right? I'm not sure if I have any protection in this. I might or might not have. I think I have an external protection module, although who knows? As I've said, I've done this about a half year ago or even more, and I've started building it a year ago and I finished it half a year ago. So that's kind of, and I have used it and it works. I can vouch for it. So we have the battery, right? And I'm switching the negative to system ground, right? The whole thing has one ground. And so this is basically this power switch here. All right. Let's actually put it in the dot mode because that looks kind of cool. Next up, right, I'm taking basically almost directly, I'm going with the battery plus voltage into the booster, which is this module over here, So these are very good, very efficient, and the reason I'm doing this is to obtain a very smooth and steady and precise and non-varying 5-volt rail. Right, so as you may know, the Arduino boards have a little linear regulator on board, which obviously is quite silent and quite stable and whatnot. And so no matter where the battery voltage is, right, because that goes from 4.2 to, I think it cuts out at, yeah, I must be using some protection because otherwise it wouldn't cut out, right? So I'm definitely using some protection. Remember, kids. Anyway. Exactly. So we're taking the battery voltage, whatever it would be, like 4.2 down to, let's say, 2.8. I'm boosting it up to 9 volts, feeding that into the voltage in and to the VIN port on the Arduino pin. Then that has an internal regulator. I think I can even show it. No, it's hidden. Anyway, that has a linear regulator, and that makes the 5-volt rail that we see over here. Right? So then I'm taking the 5-volt rail, and then I'm also getting one analog pin back to the battery so I can measure it and have that view where I show how much of the battery is left. So I'm showing that at the beginning at startup, and when it gets to 0 bars, I switch the mode and go into the battery mode to alert the user that the battery is about to die out. Okay, what else? We have the mode switch button, which is connected to digital pin 2, which is an interrupt pin, I think. I'm pretty sure. And that has an internal pull down resistor, so basically whenever you press it, oh no, I actually haven't used that. So I've pulled it high artificially with this externally, with this 500 ohm resistor. So whenever I press the button, it actually shorts that down to ground, and we have a falling edge, which I think triggers the interrupt. I'm not sure. We'll check the code. As I've said, I haven't looked at the code in half a year, so. But I think that's what's happening, right? So this stays at 5 volts or whatever but it's 5 volts, right? It stays at 5 volts, you press the button, it goes to ground, and then the Arduino detects it and interprets it and changes the mode, or does the special features such as device under test and reset and whatever. Okay, so that's all good, that's all fine. And then we have the INA219 module, which is this one here. You could also use an INA226, and I have used it in the iPod Hi-Fi restoration. That one has quite a bit more precision and quite a higher voltage tolerance. However, with the resistor that it gets supplied with, it can only measure up to 800 milliamps. And I don't want sub-milliamp precision, which that does offer, but I do want a higher current handling capability, which this offers, right? So the fuse in here is 3 amps, and I think I measure up to 3 amps because that's the limit, but it actually can measure higher, but you risk frying it. And I have fried at least 2 of these while testing them. Anyway, that's something else. So I have the I2C lines going to the INA219 module. So these are for serial clock. Which one was it? So for serial clock we have A5, and for serial data we have A4. But again, this we'll see in the code as well. These 2 lines, I haven't depicted this, also go to the I2C display, right, obviously. So these simply branch off to the display. And I think we're done with this. So now going on to the power measurement. Alright, so here I'm not too happy with the way things turned out, right? So the one major drawback with the INA219 and 226 is that they are only they only accept voltage measurements in one polarity, right? So you can't measure AC voltage and you can't measure DC voltage in the wrong polarity. They fry up immediately. I am working on an alternative to this, so I've gotten this module here. This one here. So this MCP chip, and this is supposed to measure both ways, right? So a differential signal. It can measure up to, I think, 3 volts or even less, so you would need some resistors and some shit, but it is very precise. I think it's 16 or 22 bits or something ridiculous. I'll put it in the description as well, and so you can have a look at that. And if anyone has actually played with this and made a power monitor using them, or at least the voltage measurement part of a power monitor, then definitely hit me up in the comments. I am fabulously interested. Alright, moving on. So what I've done to mitigate this is added a fuse, right? In this case it's a 3 amp fuse. So again, this also helps not to overload the system, but a short burst of more than 4 amps, of more than 3 amps, or more than whatever this can tolerate will not blow the fuse fast enough to protect the chip. The reason why the fuse is here is to try and protect the chip. Again, I'm not sure that's going to work, but again, you could buy these modules. So these power monitoring modules for like $1.50 or something. So I do have a stash of them, and if it blows, then it blows. It's not that bad. As I've said, I did fry some other ones, but not due to reverse polarity connection. So the way you're supposed to measure this, measure currents and power with this, is connect the plus rail and pass it through it, right? Measure the current on the high side, and then connect the ground. Alright, so I found some goodies. I found the calibration cables. So those we're gonna go into a little bit later. Yeah, so basically what I was going for was this. So this is basically very good disambiguation of how this INA219 module works. So it has 2 pins labeled voltage in negative and voltage in positive, right? And the voltage measurement is across voltage positive and ground. Is it? I think. No. Voltage, I'm talking shit. So V bus is measured between voltage and negative, right? Which is why this is the positive. And ground, right? And I wrote here plus diode drop. I'm no longer using the diode, or am I? Yeah, I don't think I'm using this diode anymore. Right, so initially I used this, I think, to protect against a reverse polarity, but this proved to be highly inaccurate, right? So this has a very big drop, especially at the extremely small currents it would be handling. So at some point I did, am I using it? No, I'm not. Okay. So at some point I did actually have a resistor between plus and negative just to create some current across this diode to make it a bit more predictable. But that ended up not working nicely, so you can cross this out. I have not used it, so not a good idea. Alright. So that being said, this is the rough setup that I'm using, right? V negative. And then this would be the negative connection up top, and then these would be the 2 current path connections. And again, between voltage negative and ground is how the thing is measured, which is quite unintuitive. I have no idea why they did that, but anyway, it's the way the cookie crumbles. And also, if you just leave it like that, as it was over there, you will always get like a bias of about 1 volt. And what I also had to do is put a 43.2K pull down resistor that kind of, I have no idea how not nice and not proper this is, right? Because this had a bias of 1 volt, and I'm not sure if it was needed for anything, but I've pulled it down to 0. So in some instances it does actually display 0.001 volts, right? So it's at the peak of, at the limit of 1 millivolt kind of. But it pulls it down enough, and I can measure the voltages okay, and I can measure the currents okay, and it does indeed add some extra current, right? So this will actually pull some current. When you put about like 25 volts or something, it will actually draw some current, but it's quite small, so it's fine. Okay, so that being said, I think we can screw this back together. And as I've mentioned, right, all the parts for this will be in the description, right? I recommend these buttons. They're very nice. A bit small, right? So if you have big hands, probably go for... I think these are 12 millimeters. Could go for 16 millimeters buttons, but these are fine. The fuse holder is awesome. So I'll definitely put these in the description. And if they become unavailable, so for example, the fuse holder I can't put a search link for. Have to put the exact one I got. So when they do discontinue the product or something, do let me know and I'll see if I can update them. Alright, so this is always quite a bit fiddly to put together, but I think... Which goddamn way was it? Yeah, I think it was this one. And as you may also notice, the ring light of the mode button has gone off and the display is now dimmer. So this also goes into a minimum brightness mode, mainly to save the OLED rather than battery. But this LED here uses quite a bit of current, right? So a few milliamps at least. So yeah, why not? So you just wake it up by pressing it. Alright. So next up, let's actually arrange the cables a bit nicer here. So next up, we're going to go to the computer and go over the code. And then that'll be pretty much all. Okay, so I actually forgot to draw out the power loss detector. So to get a power loss detector, we need two things, right? First of all, we need a reservoir. Fuck, I'm drawing the wrong thing. Number one is you would need a reservoir capacitor from the 5-volt line down to ground, right? So this is, in my case, 1000 microfarads. Okay, and then the second thing, you have an analog pin, can be whichever one. You have a resistor in series with it. In my case, I think it's 1K or 500 ohms or something like that. And you have another capacitor. Right, this one can be a lot smaller, right? I think I'm using 22 microfarads, if I'm not mistaken. And so what happens here is this is not what this thing is doing. I have an older solution and I also detailed this in a separate video. But basically what we're doing is we have an interrupt that's called every 100 milliseconds, I think, and it checks, is this capacitor charged to, let's say, 3 volts, right? The analog value for 3 volts would be, I don't know, the integer value would be, I don't know, 700, 600, who knows. So 1024 is equal to VDD, let's call it, which is 5 volts, right? So 3 volts would be whatever. And so it checks, is it charged to 3 volts? No. Then we charge it. Then it turns A0 to an output and pulls it high. So shoves 5 volts into the capacitor via this resistor. Next 100 milliseconds, it checks again. Is it charged? No. Then it keeps charging it. At some point, it will get to that degree, to that value, right? And at that point, it will stop, right? And it will ask, is it larger than 3 volts? Right? Which is, let's say, for the purpose of this video, is it larger than 600? And it might be a tiny bit larger. You need to finesse these values, right? You can ask if it's larger than 800, for example. So we're aiming to keep it at 600. And we ask, is it bigger than 800, right? And if the thing is powered, then the answer should clearly be not, because as soon as we're close to this, we stop charging it, right? But when the power drops, right, and VDD drops, then we'll at one point get to be like at 2 volts VDD, right? And then at that point, the 3 volts the cap is at will actually evaluate to 1024, right? Or a very big value. Will overload the ADC, right? And that is not nice practice, but I have used it again in these for at least half a year, and it is fine. And especially if you have a pretty big resistor here, it's not going to be a problem. So yeah, so that's how the power loss is handled here. And again, the video is at the top, and I'll add it in the description as well, probably. That goes into more detail on this. All right, so then in the interest of time, I'll gloss over a lot of the stuff, and it is pretty thoroughly commented, so this is the version I'll upload to Git, so you should be able to understand most, if not everything, pretty immediately. Very quickly, I'm going to go over some of the highlights. One of them is this library for EEPROM wear leveling. So if you imagine the EEPROM being a simple array, right, what you want to do is not write your values and change them over the same cell, because that will wear out the respective cell, and they have, I don't know exactly what the ratings are for the Atmega 328P, which is the microcontroller used in Arduino, but it's somewhere between 10,000 and 100,000. So you technically could just always write to the same cell, but it's pretty bad practice. And yeah. So what this basically does, this library, is it writes for example, in this case I'm using 3 variables, amount of indexes, which are the display mode, the milliamp hour figures, and the and the milliwatt hour figure. And so what this does is it takes, assuming they're all the same size, which they are not, takes the initial values and then writes the next updated values on the next cells, and then on the next cells, and on the next cells, and has a clever way of remembering and figuring out which is the last cell, right? And when it gets to the end, it'll start writing again from the bottom. It'll probably erase everything and then start writing again from the beginning. So you basically need to give it a layout version, and what this does is it tells it that you are using these 3 indexes of these particular types, right? If you, for example, decide to add another variable, you would have to change this to 4 and increment the layout version. And what this will do is it'll initialize everything to 0 and basically change the spacing from 3 blocks of 3, for example, 2 blocks of 4. Right, and that way it'll be able to figure which is the last block and stuff like that, like the storage alignment, so to say. Okay. The rest of the stuff is pretty straightforward, and I have covered the OLED and the INA219 in other videos. I'm allowing a maximum voltage of 25 volts and a maximum current of 3.1 amps. You can actually read quite a bit higher than this, but you can fry your chip, and yeah, that's obviously not helpful. I'm using all the variables, almost all of them, as global. I'm declaring them as global variables. This is pretty, I don't know, it's not common practice and it's not recommended, so to say, but for a simple project like this, I think the added benefit of not having to constantly allocate stuff on the stack outweighs the debugging penalties you pay for having global variables. Plus, I can't step through this, like the debugger is pretty much just a serial monitor, and that's all. Anyway, also worthy of note, I'm saving this entire uint8, so byte array of numbers, in progmem. So this is basically the same memory where the code is stored, and you can actually access it to store different variables, such as this one, right? So this would be the offsets for all the current readings in increments of 100 milliamps. So for example, for 200 milliamps, we need to add 2 to the reading, right? So a raw reading of 200 milliamps would be displayed as 202 milliamps. Alright, that covers that. Then more variables. What are we doing at the beginning? So we're initializing the serial interface in case we're using that serial output mode. Declaring all of this. We're attaching interrupt pins, right? So you might have noticed at the top we've added these 2 libraries for timers and for interrupts. I don't think you need a library. Yeah, no, so you don't. So attach interrupt, and we're attaching the register, the button 1. And button 1 should have been defined, or was it? Where was it? Button 1 here. So digital pin 2 is attached as an interrupt. on the falling edge, right? Remember I showed you that it's tied to 5 volts, and when you press the button it goes to ground. And it will call the function register button press, which we'll get to in a moment. I'm attaching the timer interrupts, right? So call the milliamp hour, milliwatt hour calculator every 1 second, or 1 million microseconds. Is this? Yeah. And power loss detector every 10 milliseconds. So quite often we check that. Here we initialize the display, the power monitor. We show the battery right quick, and initialize the EEPROM controller. In the loop, right? So the loop is pretty short. All that we do is, if the button was pressed, right? So let's see what register button press does right quick. So interrupt service routine. Register button press. If millis is smaller than 500, this means the system has not been on for more than 500 milliseconds, then we get out of this, right? Because in some cases I would have had problems with the initial button triggering very quickly at the start of the system. So that basically avoids that. Use it only if you must. Then we're doing some debouncing. Basically we're recording the time of the last interrupt, and if 2 button presses occur quicker than 300 milliseconds, have less than 300 milliseconds between them, then we discard them, right? Because when you press the button, the contact can actually bounce a little bit on it. And so basically that is what that does, right? So in very dodgy electronics, you'll notice that when you press the button, sometimes it registers as 2 clicks. So that's what we're preventing here. Also, if dim mode is enabled right after a lot of time has passed, we don't do this. We just update the time of last interrupt, and the display will wake up, right? Only if we are not in dim mode will we flag the button as pressed. All right. So if button press, where was it? Yeah, I think we should go a bit faster through this. If button pressed human interface controller. So basically what this does is it handles the button press, and first of all we do this whole thing. It's pretty long. So this whole function here is what happens if the button is pressed for longer than just like a simple click, right? And in this case, long hold duration was like 400 milliseconds or something like that. So depending on the current display mode we're in, we either enter device under test mode. So for amps and volts, amp, watts, we do this, right? Please note that there's no break here. So if the case is A, then it does this, which is basically the empty instruction, and then goes on to the next case. Serial and the amp hour view reset the values, and then the other one resets the maximum. And what does this one do? Oh, there's actually a little hidden thing in the battery mode, so it tells you the on time. Okay, so that's pretty much it. Let's go back to the top. Oh my god! All right. So in 100 millisecond intervals, right? This is what this does. We first of all acquire data. So we don't want to acquire data as fast as we can do it, because there's absolutely no reason, right? We acquire data, we display it, right? And the current display mode decides how we display it, right? So the data acquisition is completely independent from what happens on the screen. And all of what this does is basically show an empty battery nag screen, right? So basically when you're using the device and the battery becomes critically low, it'll take you to this display. And it'll only switch to it once, right? So that's what this variable does. All right. Where do we go from here? The power loss detector, I'm not going to go into this in this video. Check my other video on this. I'll put it in the top right corner. I don't know what the goddamn hell is this. Show emoji. Oh, crap. Anyway. Right, the EEPROM controller, maybe talk a bit about that. So if we tell it to save the state, it's first of all gonna check if what we have saved already is different from where we are on now, because if it's the same, it makes no sense to overwrite a cell with the same value, right? So we avoid that, right? We minimize the number of writes we do to the EEPROM. Reads you can do however many you want. Writes is the limiting factor. We also condition the variable, and this is very, very, very important. If by some accident this variable has become 15 or something, and we save it, right, and then the next button press can't take it back to between 0 and 5 or whatever we have, then the device will be forever bricked, right? So this is very important. We don't want to save corrupted values. So we ask for it to be greater than 0 and smaller than serial. We actually have values bigger than serial, which is the battery mode and the screen off mode, but we don't want to save those, right? We don't want to boot to the screen off mode. Alright, and if we do, then we go EEPROM where-leveler.update. We give it the index display, so this would be 0, for example. You could just write 0 here. And current display mode. And we turn the LED on to display that we are saving something. Then we'll get the milliamp hours and milliwatt hours from the EEPROM controller again. If they are different from the values we are saved, only then will we actually put those in. So update does bytes, right? So 8-bit words, for example, uint 8t, for example. You could do with update, and put is for bigger variables. So milliamp hours, what is this? Let's check right quick. So milliamp hours. Where is it? Milliamp hours. So it's uint32, right? So 32-bit unsigned. Okay. So those you would use put for. Open would again just get the display, the current display mode, and if it is larger than serial, we are going to revert it back to 2, right? So we're going to condition the values so that no matter what happens to the EEPROM, we cannot land in an unknown state that we potentially cannot escape from. What else? Let's go to acquire data. All right. So we have a device under test mode, right, that injects values. If we're not in the device under test mode, we basically get the raw bus voltage, the raw current. We condition those so the current has one too many decimals, is too long, right? We're going to ditch the last value, and I'm rounding it, right, to the net, basically rounding it here, right? So if the last digit is 5, then we're going to round to 1 up, and if not, we're just going to ditch the last number, right? So for example, 7 would be taken to 1, 2, 4, and 4 would go to 1, 2, 3. All right. And yeah, whatever values are very small, we're going to round them to 0. I have no idea why I put this in, but there should be a reason, so yeah. Just going to leave it as is. We're also going to separate the sign, right? So negative current, because when we're displaying it, we want to handle the numbers as positive. You'll see why later. Exactly, here we're using the offset, so PGM read byte near, and this weird thing, right? So voltage cal data is the start of the prog mem area, so voltage cal data, right? And we want to read the, for example, for 100 milliamps, we want to read number 1, right? So, or 1 volt, sorry, 1 volt. We would want to read this offset, right? Because it's in 1 volt increments. So we read this, right? So we read PGM, right? whatever address this has, plus the voltage divided by 1000. So 1 volt divided by 1000 millivolts divided by 1000 gives us 1, which is the index of this, right? And so in this case, we would add 40 to our value, right? In the case of the voltage, and in the case of the current, we go in 100 milliamp steps, so we divide it by 100. All right, we filter the values, right? So this is also something that I'm quite proud of. In the way we do this, we have an accumulator, right? So the way I thought of this is basically you have a value that you're displaying, right? Which is the filtered value, and a value that you are receiving from your analog to digital converter, right? So if, for example, my filtered value is 100 milliamps and the values I am receiving from the ADC are 98 and 102, over time, the value 100, which I'm displaying, is indeed correct, right? I'm not making an error by showing that value. It is filtered, right? And it is also correct at the same time. It's the average of those two values. But if I'm receiving 95 and 102, over time, this accumulator will become negative, right? And so if the accumulator is negative, is smaller than the negative of the right, because it's the other side. And all of this you could simplify, but I made the code in a way that it's most readable, right? So if the accumulator becomes too large, right, either in the negative domain or the positive domain, it means that we're displaying a value that is consistently off, right? So we basically need to bring it closer to the value that that we're receiving, right? So over time, it will. First of all, if what was it? Yeah. So if the difference from what we're displaying to what we're getting is bigger than this maximum instant deviation, we're just going to update the value, right? So if we're showing 1 amp and all of a sudden we get values, we get data for 2 amps, we're going to immediately do that. We're not going to just go in steps of 1, right? But once we get to 1 amp, the fine changes will slowly follow the actual data, right? In steps of 1 until the filtered value will be close to the raw value and the accumulator will basically cancel out to 0 and will never grow larger than max total deviation. I hope this makes sense. Then we're going to use the display controller, and here is where all the magic happens, right? No, actually, not here. All the magic happens in this divide by 1000 function, right? So for example, let's take, for example, the amps case, where we're just displaying the amps. So we're writing a big A somewhere, we're setting the text size to a bit larger, and then we're going to print this reading at these parameters. Again, this is center and print. We'll probably also go into this, but the main topic of this is divide by 1000. This is the thing that I'm most proud of and I've worked the most on, as I've said. Well, yeah, I think from the whole thing, programming effort, I think this divide by 1000 was the... Anyway, so we give it the filtered current, whether it's negative or not, right? Because this always has to be positive. We have 6 spots with the big font on this screen. And I have no idea what this is, to be honest. Oh yeah, and we give it the current. Yeah, correct. So we're displaying the current. I have no idea why we're doing this now. So we also tell the divide by 1000 function whether we're displaying current or voltage. I don't know. Oh yeah, I think the so this function also does the over limit, and so there's different limits for current and voltage. I think that's why it's happening. But in any case, let's just go to that. So divide by 1000. Here we go. Current, voltage, wattage. All right. Shoo. Oh yeah. See, so that's why we do it. So current, voltage. So max allowed current, max allowed voltage. So we return this over limit. And again, do note that it's 6. So we need 6 spaces here. So 1, 2, 3, 4, 5, 6. Right. Alignment is very critical. And again, we have 6 spaces to display it. Right, in the mode with the milliamp hours, we have just 4 spaces, so it's a different thing, but I'm just going to go over the 6. No, actually, let's go over this because this is a bit more tricky. So same thing, we display over limit when the stuff is too large, and then you get this. Right, so you have a number that's length 2, let's say, right, because I have the examples here. Right, so negative sign, I put a negative. Oh, by the way, these F's mean, so for example, doing this means that at every startup, all of this text, right, this negative sign, these 3 characters, everything will be loaded into RAM, which is extremely wasteful, right, and especially if this code uses pretty much all of it. Oh man, alright, but it did work. So 98% of the program space and 81% of the RAM, so yeah, quite tight. So we display the negative sign if the number is negative, and then we start dividing the stuff, right? So for example, 98 divided by 1000 should be 0.10, right? And we have 4 spaces, so 1, 2, 3, 4. Same thing, right? So we basically go over all the decimal points, see if we need to round up, and do it accordingly. And yeah, this took quite a long time to iron out all the bugs from, right? If you see something that's wrong, then do let me know, because, yeah. Alright, what else? What else? Divide by 100,000 or a million is this. This is just for the values that are, I think the current is in microamps, and I want milliamps or nano, I don't know, anyway. And the format and print large number basically does what is shown here, right? So it basically adds padding to make the number fit in the middle, right? And in some cases, right, it needs, it also will need a half a space external indentation, right? Because you can see, right, you can't center the line, right? So that also does this, but again, this you can check in the Git, the full implementation, and maybe perhaps also important the milliamp milliwatt hour computer, right? So this gets called every second. Right, there's stuff to be aware of here. So for example, this did not work in this IDE. I have no idea why, but it really didn't. So what I'm doing is basically adding the milliamp seconds, right? This is basically what we're computing every second, obviously, right? The filtered power, I'm also filtering a little bit. I'm dividing it by 1,000, right? Because I think the power is not milliwatts. It's nanowatts or some shit. Anyway. And I'm choosing a big value, right? So when the milliamp seconds gets to a value that's large enough, we're going to start dividing it, right? There's no point in dividing it by 3,600 when it's 5, because you're just going to get 0, right? Arduinos are very bad at division, right? And especially there's no floating points there. I mean, there is floating points, but they're slow, they're weird anyway. So we're doing all of this with integers. And that's fine, right? Because we're adding to the milliamp hours the milliamp seconds divided by, right, 60 times 60. 60 seconds, 60 minutes, 1 hour. And you could think, all right, yeah, but this is going to give us basically the floor of this division, right? So 3,700 will still give 1. Well, for this, we're going to recirculate the remainder, right? So what we haven't put into milliamp hours, we're going to leave in milliamp seconds, right? And this way, we're never going to be off, right? We're always going to keep putting that value back and recirculate the remainder, is the best way to describe it. And we do exactly the same thing for milliwatt hours, and that's pretty much all. Again, register button press, we talked about the human interface controller. Again, a lot of code. I have a little function to turn the lights off. Number length, depth, set brightness. That's pretty much all. Right, so I hope this was clear and concise enough. It's very difficult, so either go too in depth or too over the top, right? For example, Great Scott does these extremely quickly, goes over the code extremely quickly, so I hope this is a bit more understandable, but anyway, you can leave comments down below, and I'll see what I can do. Alright, have a good one, guys.